Hi everyone, it's Judy. Welcome back to the Ontrack Podcast. Today's guest is a veteran PCB designer who's had the rare insight and experience to work alongside PCB fabricators and assembly. He actually works for a dynamic Eastern Washington EMS provider, and he's going to tell you what he sees from an insider's perspective about how you can be successful on panelization, copper pullback, and make you look like a real pro. Enjoy this podcast with Kelly Dack, and I'll see you on the other side. Welcome to Altium's Ontrack Podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Hi, Kelly Dack. It's great to see you. Thanks so much for joining us today on the Ontrack Podcast.
Likewise, Judy. Great to see you. Wasn't it a fun week we had at Apex Expo?
Such a blast.
Yeah.
And by the way, definitely throwing the video in the show notes. We did a recap video there, and you and Andy Shaughnessy from Design 007 had a little jam session that we caught on camera. So you were kind of the music track to our recap video of Apex, so that was really fun.
I appreciate you and Ben making us sound good. Yeah, that was. I don't even think we knew you were recording. Otherwise, we would have hit it out of the park.
Here was my contribution: the shaking of the little egg.
You did the egg shaker.
That's as far as I go, people. Well, since we recently saw each other and we were talking, you did a podcast with us really early on, Kelly, talking about what is PCB design. And I know you have a wealth of knowledge because having been a designer for all the years, being a CID Plus instructor, you have also worked for a fabricator, and now you're working for an EMS provider. So I think that you know where all the bodies are buried. I like to say I feel really well rounded as a designer. It's almost kind of a luxury. You talk to a lot of PC board designers, and we get to. I teach with EPTAC Corporation, the CID program also, and we always ask our candidates for the CID programs. Out of all you engineers or all you designers that are sitting out there, how many of you have ever visited a board shop or an assembly shop? And we see so few hands go up. To be able to be a designer after all these years and have worked as a captive designer, and then to be able to sit down the aisle from at a board shop, doing design, helping designers, reaching out for DFM, to be able to sit down the hall from the people that are actually doing the work is just, it's a luxury. You can see everything you've been talking about. You can see and put together everything you're designing for. Yeah.
And I've had the luxury to be able to do it both in the fabrication world and assembly world. So it's really cool.
I think it's a really great, like you said, rare, experience. Although more EMS companies are having captive designers, which Rocket EMS up in Silicon Valley, their designers sit adjacent to their program managers or their project managers, right? And so, I think that's invaluable for their throughput and getting things done the right first time. Right the first time. Communication, so we were talking about this topic that does not seem all that sexy or complicated, but boy, I've learned from you that it can get a lot messier than I thought, which is design for manufacturing in regards to PCB outlines.
Yes.
Right? Just the footprints of the board. So what would you say are, the the biggest disconnect, designers have, say, between what they're laying out in their CAD tool and what they think is happening in fab and assembly?
Well, it's interesting because my eyes were opened. I was enlightened. I had an aha moment the moment I stepped away from the captive design world and into the EMS or fabrication world, and that is that I got to see designs coming in from all over the world, all over the country, and I got to see the work of our fellow designers. Excuse me, and I gotta say, you're all doing some really excellent stuff out there, and there's a lot of tendency to push the envelope and make the designs as tight as we can. But along with that, we're hearing grumbling of why did they do this from the board fabricators. There's a lot of stuff, a lot of DFM challenges that still need to be addressed by designers. So one of them that I deal with almost at least once a week from some customers is the fact that we have to take this one-up board that's been designed and probably prototyped, and we have to move it into the assembly world. We have to panelize it. We have to create an array, because nobody in volume, this is what designers have to understand, is in volume, we don't build one-ups. It's not like we're in the lab anymore. We have to move these products to volume production, and that means we're got to consider panel utilization. So we're going to create arrays, and in order to create arrays, we have to have certain parameters, and the parameters that we're running into that are causing most of the problems are something we term copper pullback. We have settings in our software, right, for pulling back the copper. So that's what I'd like to talk about today is, board edges and what we can do to this seemingly mundane subject of board outlines. And let's look at how important they really are, what matters and what doesn't matter. How about?
Yeah. So for our listeners, Kelly's going to pull up some slides here, but if you're listening by audio, don't worry, because I'm going to throw his PDFs in the show notes.
Right on. We won't leave you hanging.
Okay. And he'll talk through everything he's showing right now, but just want you to know.
Yeah. And I think you might be able to see my cursor point here, because, of course, I can't talk without a cursor point. So what we're showing is a board edge condition here. I've got a 3D view of a generic board. We see a little fiducial on here. But the thing that is causing us problems in the EMS industry is we've got to get this single board design into production. And the way that we do that is by panelizing it. And to get to the point, we cannot panelize boards and cut board edges that have copper pulled or copper placed too close to the board edge. So what I'm showing right here is you can see some copper and you can see the board edge, and we're seeing a little bit of what we're calling copper pullback. And if we don't have enough, our cutting methods are going to potentially cut into the copper and leave exposed copper. So we want to avoid that.
And what's problematic about that, right? If you're putting that in a metal chassis, it's going to short, right, to the chassis, right?
Short or corrode.
Or corrode, right? If it's exposed to oxygen, it can corrode. I mean, there's lots of problems that occur.
Yeah, quite a few bad things that can happen.
Okay.
So what we ideally want to do is have enough pullback on these boards, copper pullback, so that we can choose a panelization cutout method, for lack of terms.
Yeah.
So there's several
let's talk about
several operations.
Go ahead. Yeah, I'd like you to talk about what different ways, of course there's the standard way of like routing them out at fabrication, but what other ways have they developed, or scoring? What are different ways that they cut boards out of a panel?
at Apex, you could walk the show floors and you can see lots and lots of equipment. And there are machines there that are taking care of this panelization process or depanelization process. Some of the oddball ones you see are like you can cut boards now with water jet. You have been able to for a long time. The real creative. I haven't utilized any of that technology, but it's out there. Just think of it. You can get a real fine jet of abrasive fluid that will cut through boards. What's the advantage there? Maybe it takes away dust. And there's certainly no burning or smell like you have with laser. Laser's another one. Very common, especially this year. I talked to lots of folks. What an LPKF, check them out. Tons of new quicker labor saving, quicker lasers that will excise a board. Why would you want to use a laser, for instance? Sometimes my pile of boards here. This is an example of a rigid flex circuit. This is a rigidized flex circuit here. Not too much stability when it comes to component mounting. So you're most likely not going to use a traditional router type methodology on this. So this is very lasers are being used in excising or cutting out flex circuit or rigid flex more and more. Some of the traditional we get into the traditional cutters. Routing is a methodology where, well, for instance, this board I was holding up here, this is a routed, we'd consider that a routed board. And typically we will have little tabs that will retain the board within this overall panel so that it can go through its processes of assembly. And then at a certain time, this board will be excised, hopefully not like this, where somebody just pulls it out.
Yeah, you don't just pop it out, right?
You don't pop it out. We have special tools for that. But
do those have little mouse bites on them, or how are those being, the ones that you have in your hand? So he has these round boards with tabs on the end. Do they have mouse bites? Or are they scored? Like, how are they in that panel?
They can. We have a couple details I'll go through a little later.
Okay.
But we do different methodologies. And back to copper pullback.
Okay.
In fact, let me advance to that slide here real quick since we're there. Boom and boom. And so here's exactly what you're talking about, Judy, is these holes can be perforations drilled at the top and bottom, or the top or bottom. You can use one row or two rows that will guide the break or the cut of the retaining tab. Now, if we don't have enough copper pullback, there's some problems that can happen. Check this out. When we get a customer who's done their best to get as much copper on the board as they can, we don't have enough room to put these small perforations, right? So we're going to ask the customer or provide that the supplier that's building this board, we're going to enable them to cut this copper out. And that sometimes causes a problem with our customers. They don't like any manipulation of the copper. So we try to encourage our designers to pull that copper back.
Right. While they're in the midst of the design, right?
Yes.
So it's not done post-design and there's all those calls going back and forth.
Right. I'll talk about, let's not miss a few. There's just a few more excising methods or cutting methods we can talk about. One we don't want to miss is V-scoring. If there's not enough room to cut these large slots in the board, you can see a board like this this panel is not utilized very well. The yield is a 1, 2, 3 by a 5 array, and we could probably do a lot better job of getting an extra row or several more parts in this array if we pack things together. But notice this is a round board, and there's inherently a lot of waste of panel material with a round board. But take a board like this, for instance. So whenever we take a board like this nice square-shaped board, this is ideal. There need not be too much waste at all, material waste on a board like this, because now we can pack these board edges together, and we don't have to have a route between them. We can use, if there is enough copper pullback, we can use a V-score method. So let's take a look at that for a minute. I got a slide that
So while Kelly pulls that slide up for you guys, what he's showing right now is a board that has a square rectangular, and they're almost like butt joints, right? And then they're V-scored between those butt joints. So obviously a lot less material waste, and as Kelly said, you can get more on the panel. But they still have to have the appropriate pullback. There it is.
So here's your V-score detail. They're gonna be different from supplier to supplier. Typically, we as designers, if we're designing panelization, we'll go with a 1/3, 1/3, 1/3 rule, we like to call it, which this is not necessarily, but 1/3, 1/3, 1/3 is basically, if we have an 062 thick board, we'll V-score at 30% of that depth, make it I'm bad at math, 20 thousandths and a 20 thousandths web, and then on the bottom side also make it 20 thousandths. In this particular case, our manufacturing engineers, they desired a 12 thousandths web, so we made the adjustments. But again, this is something that's very line dependent. Our designers typically won't get into panelization unless they have an in-house assembly operation. That's another luxury. If you have if you're working for maybe a larger company that can do your prototypes, you send out your boards, and then you can have them you have an automated assembly line, you're probably going to be one of the designers that's going to have to create a panel. So a lot of these panels we created for our in-house assembly line. So you're going to have to learn what it takes to excise these boards, and to run them through what type of rails and other features that are needed for automated assembly.
So then what you're saying is, normally as a designer, you would not design a whole panel structure because you're going to be doing one-ups, unless you have in-house. Now, so how do you know when, as a designer, you should panelize, or is there any point at which you as a designer need to think about that? I mean, obviously you have to think about the copper pullback and all that, but is there any scenario in which you're involved in stepping and repeating your design?
Sure. Let's get back to board outline and shape. You can see that if you're driving for low cost on your assemblies, that a rectangular shapes typically have much better panel utilization. Material utilization. So you're going to have a much lower cost, most likely, on a rectangular board. However, odd-shaped boards, like this is an old rigid flex I pulled off a show floor. This is several boards that are all interconnected by flex. But you can see that you pretty much are limited to how much material usage you have on a board like this. So as a designer, if you are sending your board designs off to an EMS provider for assembly, just design your one up. Be conscious of your board shapes, push for rectangularity, but
if you have that luxury,
sometimes
right?
that's, if you have that luxury, sure. But know that your board supplier is going to have to put the shape, whatever shape it is, into a panel form with rails so that it can run down the automated assembly line.
Right, so the rails, it's like a frame that they create at assembly, right, where they can put that one up in a frame so it could run through the conveyorized system, right, to the pick and place in the oven and all that kind of good stuff.
Right. So, for instance, here's a rather large board. This board takes up the entire working panel, with the exception of some rails here that we've added just to the side. That's all that was required on each side. Rails.
Very cool.
Right? So this board can fully run down the line, be happy, and they're V-scored. The rails are V-scored, so when the final, it goes to the assembly processor, goes through inspection, all the parts are on the board. We take what's called a pizza cutter for our V-score world. I wish I had a picture of it, but any of our viewers can look online and look up PCB V-scoring, or excising is a 25-cent word for V-scoring, and you can I think you can even Google pizza cutter, because that's what it looks like. It's a round knife that will appropriately go along this edge and just peel the rail right off. These are not rails. If you ever see somebody grabbing a board like this and breaking it, say no. Don't do it. Because that, you can see how much force I put on this board.
If you break them out by your hand, it creates torque. You can
torque or stress.
You can pop components off, right, Kelly? And
absolutely.
What else? What other kind of damage? Just don't do it. Just say no.
Just don't do that.
Okay.
I agree.
All right. Is there anything else you wanted to add there? Because I have a million more questions, but
well, maybe we can talk about ask your questions, and then maybe we can get into how we're going to define our board edges.
Okay.
What's a reasonable way to dimension and tolerance and consider?
That's where my brain's going. But the first thing I wanted to ask you is, you said don't worry about panelizing, right? Except if you're designing the board, and then you're going to sub that out turnkey, right, to an EMS provider. And so you're saying if it's turnkey, that they will take your Gerber data, they will add those rails, right? I wanted to clear that up because it's not done that much anymore, but it used to be where you have your fabricator and you do your bare boards over here and your assembly over here. In which case you would need to have it panelized at the fabricator, but most things now go turnkey through the EMS provider. So
it can. It's a sticky wicket depending on who's doing it and where. With a lot of volume production, it's still going over to China, and it's being assembled. It could be assembled in China, or it could be brought back here, or south of the border in Mexico. So we don't really know, or designers don't really know where their boards are going to be built. So it's a matter of cost. Everything is cost.
Right. So I'm just saying, I'm thinking here, and again, not a designer, but if I'm a designer and I'm listening to Kelly and Judy talk about this, I'm like, okay, pullback, check. Do I put the rails in or not? And then Kelly's saying no. And then, but, where's it going, and how do I know to pass that off? You and I talk about this a lot. Pass this off in an effective way to the next stakeholder, right? So that communication is working, and I'm communicating, and it's all getting done, so I don't have to worry about one more darn thing.
Yeah, sometimes we need to stay in our lane and allow the appropriate stakeholder freedom to do their job. So it's very natural.
So
it's very natural.
So you've just educated us then about panelization, the various types, how you excise them. But in the end, to complete this part of our conversation, you're saying let the pros handle that part of it. So the actual panelization, you don't need to worry too much about. And now we're going to move into copper pullback, which is in designer's lane, right? Okay, right. I just want to make sure I'm tracking with you.
And we can be assured of that because it's outlined in IPC 2221 and 2222. And I'd like to show our viewers, if anybody's asked how much should I pull that copper back? You can point to these specs as an answer because these numbers have been provided by the entire industry who have pitched in to formulate these specs to be manufacturable, to be DFM. Right. So let me go find our...
for our listeners, I'll put that, the link to IPC 2221. Is that what you said, 2221? And okay.
Yeah, IPC 2221 and 2222. Let me pop this up here real quick just for a good view. I have a little statement. It's very important for the designer to consider copper to edge spacing with regard to the board edge manufacturing process to allow for optimal manufacturability, or DFM. The designer shall pull back the copper on the PCB away from the board edge per guidelines specified in 2221. And that we even give the chapter and verse. IPC 2222 to allow copper to edge clearance for any board excising operation. Designers need to keep in mind that this is minimal spacing. We never design to minimums. We want to take this as a minimum and give them any more than we can. That's reasonable. It'll greatly increase your DFM. So let's see if we can go forward here. So right out of IPC 2222, it's stating that edge spacing, except for board edge contacts, the minimum distance between the conducted surfaces and the edges of the finished board or non-plated through holes shall not be less than the minimum spacing in Table 6.1 of 2221. So we kind of got to put these two specs together, and that's why I'm showing you these here, because they're a little bit buried in the specifications. So if we start with a value of 0.4 millimeters or 0.016 inches as a starting point for pullback, let's start there, 16 thousandths. And then we're going to add to that amount, come on, advance. There. We're going to add to that, per the spec, an electrical spacing requirement. So you can see, depending on the voltage that's running around on your board, a lot of boards aren't going over, voltage between conductors. You could see that the numbers don't change much, even though the voltage goes higher and higher. So if we took a value of 4, this is what I like to recommend, just to get people to understand the concept. If we take this value of 4 thousandths and we add that to 16 thousandths, that's how we come up with a rule of thumb value of 20 thousandths. If you've heard, hey, pull your board back or your copper back 20 thousandths, that's probably where that number came from. So we see that we take the 16 thousandths that we're talking. We got the board edge, and then here's an example of a copper. It's an ESD ring in this case. It could be flooding, and then we're going to add 16 thousandths and plus the electrical spacing, which we just saw as another 4 thousandths. So I hope everybody can see that and hopefully agree with that, because this is the magic number. Oh.
And like I said, everyone that's listening and either working out or driving their car, fear not. You can go into the show notes later and see all the downloadable PDFs stuff, where you can see what Kelly's talking about.
Right. So this this is the idea, is if we can get at least, as a EMS provider, if we can get at least that 20 thousandths, it opens up our scoring or our excising capabilities or options quite a bit, and that can really reduce cost on your overall cost of your board because it affects the whole panel.
Yeah, you bet it does. These things add up quick. Okay, anything else on copper pullback before I want to have you jump a little bit into the next topic?
Let's jump.
So once you've done your pullback and all of that, what about inspection, dimensioning, and spacing? Was that, or tolerances, sorry.
Yes. Okay, so another thing we like to teach in our CID classes is what do we do with this board outline? How do we think of it with regard to the rest of the board? When we start our design database, sorry, I'm making a lot of noise with these boards over here in my pile, but I apologize. When we have let me just get one board here. I'm going to bust out one little board. Try this one. Here's a board. Now, when I started this design database, I could have started with a DXF outline or a step outline that came from mechanical that was a rectangle or a square. And most likely I pulled that in, and then I aligned maybe some mounting holes within this board outline. And then I picked a board or a database origin. And it's very normal for us to pick a database origin that's a hole. But wait a minute, working for an EMS provider, I've seen it all. Not everybody picks a hole. Some people pick this corner as a design database origin. Is there anything right or wrong with that? Let's keep going. Some people pick a point in space for their database origin.
Okay.
Have we seen that? Okay. What do any of these things have to do with the alignment of this board? Are we, when we get into dimensioning and tolerancing, are we dimensioning where the holes go relative to the board outline, or are we dimensioning where the board outline goes relative to the holes? It's a good question. And it brings me back to what is the last process done on the panel routing operation? The last thing that's done is typically the board outline is routed. So all of the holes are drilled in a panel array. I'm being quiet here. All of the holes are drilled within the panel, and the last thing that's done is the mechanical forming of the board outline. So I'm submitting to you that it might make a whole lot of sense to create or to choose a mounting hole, a through hole, as a board origin starting point. A through hole is the only thing that affects every layer of the board, and it really matters when it comes to other holes in a hole pattern from a dimensioning and tolerancing standpoint. So, yeah, that's as far as I'll go with relationship between holes and the board edge. Our most accurate alignment method, if you've done any dimensioning and tolerancing, taken any dimensioning and tolerancing class, is a single dimension between our X0, Y0 point and the board edge. And we can tolerance it different ways. So what if we have a really weird shape board?
Big mexi. What about a big rigid flex?
Yeah.
That's...
Or a big, I worked for a company and we did a lot of themed games, and we had a board that was in the shape of a Batman. It had ears and wings, and how are you going to dimension something like this? We can't dimension it with traditional methodologies where we use a linear dimension between this surface and this surface and call it a day, plus or minus 5 thousandths. With these complex shapes that we're able to do now from our mechanical designers, and we get them in 3D and everything, it's really cool, but it's almost like we've lost a way to dimension and tolerance and therefore inspect the work that's done at the bareboard supplier. So I'd like to introduce us to a spout quite a while ago, and it has to do with, if you've heard of or familiar with the term geometric dimensioning and tolerancing. As board designers, we have our own specification now for geometric dimensioning and tolerancing that's lifted out of the old ANSI Y14.5, about this thick of a book of how to dimension manifolds and just about every feature you could imagine. We live in a flat world. Our boards are pretty much rectangular, pretty flat. So we don't really need that giant spec. So they've lifted out a more board applicable version of the spec. And what I've been able to utilize really well is this concept that's called profile of a feature. And you can see, again, some geometric dimensioning and tolerancing courses are, they can be 2 weeks long. So we want to just dive into this concept because it's something we can leverage if we understand what a profile is in dimensioning and tolerancing. We can leverage that in our fabrication notes and take care of a lot of inspection requirements. So let's take a look at this real quick. If I'm proposing a fabrication note that says board edge profile shall conform to supplied Gerber data within 10 thousandths. We have a graphic here that Judy will send out for our podcast listeners. They'll show a curvy surface, could be a board outline, and shows how the tolerancing principle applies. We're calling a profile within a given dimensional range, a zone that follows the Gerber data outline. So therefore, if we put a profile tolerance of 10 thousandths on a really weird shaped curvy outline, we can communicate to our inspector that if they take the Gerber data, the nominal Gerber data, and they can now project that onto the optical comparator tables and things, they can draw this, 5 thousandths on each side, this 10 thousandths overall zone to make sure that the board outline is where it's supposed to be.
Okay. I'm glad I wasn't aware of that standard. So, how about you wrap it up and put a bow on it, Kelly?
Okay. So, all in all, there's many options for board outline machining, manufacturing considerations. Designing for the widest tolerance range, or the operation that allows for the widest tolerance range, is a really good thing for designers to consider. Let's take a look at a routed board edge. Characteristic routed board edges are machined with a high-speed router, and they typically leave a melted glazed finish on the board edge. I think we can all see that. However, if you use a V-score operation, it's done with a circular saw blade. And I don't know if you'll be able to see that, but you can see there's some little hairs on there. And if I were to run my finger along here, I could literally cut myself. I have before on a V-score edge.
Yeah.
So from a tolerancing standpoint, a tighter tolerance cut is going to be done with a router, but it's also a more expensive cut. So if we're going to design high tolerance board edges that may need to, like for instance, snap fit into the next assembly, we're going to definitely have to use a router to do that. If we're doing high volume, that we can put these boards in the pizza cutter and just zip them all apart, and they fall off, dozens at a time. That's going to be a lot more cost-effective solution. So, routing versus V-scoring. There's also stamping with special materials, the chem materials that don't use glass epoxy. They use I think a linen material within, so it's a lot less abrasive to the cutters. So again, we want to pick the appropriate tooling, allow enough clearance so that the board supplier can choose the appropriate tooling for the application.
And give them the right pullback. That's what I hear you saying, that from a designer standpoint, pull back. If you give that good pullback, then whether it's a prototype, China, US, like almost any scenario, you'll be in good stead. Right.
Always in good stead. Remember that 20 thousandths number plus whatever you can give them. The old rule of thumbs back in the old days was 50 thousandths. We used to give them 50 thousandths when boards were really large, but it's a different world now. Things have shrunk. Let's talk real quick about a concept of holes. I want to make a point here also with regard to holes. You know that a hole is just a board edge. Round holes are board edges. Did we know that? So I was surprised to find out that some engineers didn't know that they could plate board edges and get sometimes the EMI benefit of plating a board edge and stitching vias together. So you can actually plate that board edge and seal up this board and from EMI, unwanted radiations or emissions. Also, from a hole standpoint, let's consider, because a hole is a board edge, what size of hole is considered a board edge and how does that affect the machining operation? So check in with your bare board supplier and you'll find out that up to a certain range of holes is very good for drilling, and that would be the smallest drill size up to about 200 thousandths or 250 thousandths diameter are the sizes that can be drilled to create your holes or board edges. But when we're creating what we like to consider a board cutout, for instance, I don't have an example with me, but if we were to put a 1/2-inch diameter hole in here, would you imagine that would be drilled with a 1/2-inch diameter drill? Not at whatever RPMs they're using in those Exelon drill machines. They have to route that out. So from a tolerancing standpoint, we can consider our holes can be cut with higher tolerance drills. You know, typically they're plus or minus 3 thousandths we like to use. But a cutout, a routed cutout, a round hole even, that's cut with a router is going to have to take on a wider tolerance, and you could apply the same tolerance that you're using to cut your board edge, right? So if you've got a plus or minus 5 or plus or minus 10, you could expect that you would want to apply that wider tolerance to your cutout.
Yeah.
Yeah.
Makes sense.
Yeah. We talked about pullback. Let's get that copper pullback, and then dimensioning and tolerancing your board edges with values that make the best next assembly sense, values that make manufacturing and inspection sense. And that's pretty good. If we can get that far, you're going to make a lot of EMS providers' days happy.
Yeah, so you're going to make a lot of friends of EMS providers and save yourself a lot of headache and getting calls from them for you to fix things or,
Absolutely.
questions to ask, questions to pull back copper and all of that. So
it is a hassle. We get phone calls. What in this world they call them engineering queries, and we get them from our board fabricators all the time. Can we pull this copper back? And we have to typically go back to the customer and get approval. So if you can do that beforehand, people will love you.
Love you. Okay, well, Kelly, this has been so great. Thanks so much for sharing your unique insight from, someone that's, a veteran designer plus, someone that's worked shoulder to shoulder with fabricators and EMS providers.
Yeah, it's been my pleasure.
Yeah, it's been great to have you again. So A little birdie told me that you might have a song to close us out here.
Oh, yeah. Let's go all Prairie Home Companion, okay?
Okay, let's do it.
Have you ever done a Prairie Home Companion style podcast?
Never.
Let's try
do it.
Try
okay.
Okay, we got a little ditty to close out here.
Okay.
Okay. Gonna give it a try. This is gonna be in the key of T sub G for all you materials heads out there, all you laminate heads, okay? Good night, PCB designers. Good night. May you forevermore design your outlines just right. Because if you do, our PCB manufacturers are going to love you. Thank this Ontrack Podcast with Judy Warner for sharing with you this insight.
Yay!
Been fun.
Thank you, Kelly. You're the best.
All righty, you guys.
Well, thanks to our listeners and watchers for tuning in and listening to Kelly Dack. We hope you've enjoyed this. Please remember to like, subscribe, and tell us what you want to hear about next time. We look forward to being with you next week. Until then, remember to always stay on track.